Okay, so let's look at this AIDS example in the context of something called Bayes' rule. And here's Bayes' rule. We've already basically covered it. You'll recognize it if I just rewrite this as the probability of A and B. So the probability of A given B is the probability of A and B over the probability of B. And now you can see that it's a way of reversing probabilities, finding the probability of A given B from the probability of B given A and vice versa. And that's exactly what we've been doing. So there's nothing new here. So for example, in this problem, we knew that if you had AIDS 99% of the time, the test would correctly give you a positive. But what we wanted to find out was, okay, so you get a positive. What's the chance you have AIDS? And we saw that was only 1 out of 7. So we did it by this table here, right here, and we figured out that this is the total, right here, the total number of positives we said was about 7, and we added, so let's just match these up, and then you'll see what's going on. Okay, so here's Bayes. So what did we get down here? We got 6.93, right? And then we're just, what they're doing here is just multiplying this by 0.01. Okay, so now we can look at this. This looks a little bit more complicated, but the numerator here is just that, and the denominator is just this, the total number of positives. This is the probability of the true, these are the true positives, and these are the probability of testing positive if A complement, if you don't have AIDS, the false positives. So that's what we did here. And this is just the total positives. So as you can see, so we knew the probability of positive given AIDS, and we found out the probability of AIDS given positive is just the true positives, the one person basically who really, 1 out of 100 person who really has AIDS, over the total number of positives. This one and the 6 who have the false positive. Right? So that's our answer, and that's all we're doing here. So now don't worry about this too much, because you're not going to be tested on it. It's just I wanted to show it to you because Bayes, as you can do the problems that we're going to be doing in this class, using a chart. But in the future, if you had more complicated problems, you'd have to use Bayes' rule, and so I just wanted to introduce it now. But it won't be, knowing this won't be on any exam or homework. You just have to know how to, if you can get the answers from the chart, that's fine. So let's move on and go to the start chapter 7. Okay, so in chapter 7, we're going to look at the addition rule. We just did the multiplication rule, and now we're going to look at the addition rule. But before we do, let's just remember that sometimes it's helpful just to list all the possible ways that an event can turn out, all the possible outcomes. So here's a good example. Let's say you rolled 2 dice, and what's the probability of getting a total of 4 spots, a total of 7 spots, etc.? Well, how many possible outcomes are there? There's 6 ways the first die could roll, and 6 ways the second die could roll. And it's arbitrary which you call the first and which you call the second. So that's 6 times 6, which is equal to 36 possibilities. Now, out of the 36 possibilities, how many ways are there to get a total sum of 4? Well, you could get a 1 and a 3, and a 3 and a 1, And you could get, what's the only other possibility is a 2 and a 2. So you can see they're right here. It's a 1 and a 3 and a 1, and a 2 and a 2. Don't count this one twice. There's only one way that can happen. All right, so that's just the probability of getting a total sum of 4 is just 3 out of 36. How about 7? The probability of a sum of 7 would be, how many ways are there to get 7? Well, there's a 1 and a 6, 6 and a 1, 2 and a 5, 5 and a 2, and 3 and a 4, and 4 and a 3. So it's 6 out of 36 possibilities. All right, you can see them right along here, and that's the single most likely outcome if you roll 2 dice. How about an 8? So the probability of a sum of 8 is out of the 36. Here, you can get a 6 and a 2, a 2 and a 6, a 5 and a 3, a 3 and a 5, and a 4 and a 4. So there's 5 possibilities. Don't count that doubles twice. So that's pretty simple. So now let's move to the next page. Okay, so far we've looked at the multiplication rule. Now we're going to look at the addition rule. So let's remember the probability, the multiplication rule says the probability that 2 events will both occur is the probability of the first one occurring times the probability of the second one occurring given the first one has occurred. If they're independent, it just looks like this. So we're multiplying probabilities, and the picture is, okay, you have one event A and the other event B, and the probability that they're both going to occur, we're multiplying. It's a smaller probability here. It's that both of these events happen. So you can think of it as this, the probability of A and B is really the intersection of A and B. Because, you know, in ordinary language, when you say A, sometimes people think that it's all of this plus all of that. But it's really the intersection here. For example, the probability that you'll find somebody, a partner who's both rich and good looking, and smart and nice, etc., narrows it down, and pretty soon the intersection is very small. But that when you're doing the addition rule, the probability, this is, okay, so that's of multiple things happening, all of them happening. But if you're just looking at the probability of A or B, what would that look like? Well, that's the probability, for example, of somebody being rich or good looking or smart or nice or single, or and you're including a lot of possibilities. So it gets bigger and bigger and bigger, and it's basically it's the union of all the events. So if this is A and this is B, it would be all of A, all of that, including the intersection here, and all of B, which would include the intersection again, so you don't want to double count that, so you'd subtract it off. If there is an intersection, you'd subtract them off, if A and B can both happen. So if they're mutually exclusive, like if knowing A excludes B, like knowing that somebody's in this in-person class excludes you being on the online and vice versa, there's no overlap, then you don't have to subtract that off because the intersection is 0. So if 2 events are mutually exclusive, it would look like this. If you're in A, you can't be in B. Well, then you can just add the 2 events because there is no intersection. Okay. So now that's mutually exclusive. Being in one excludes the other. So, and the probability I mean, this formula still works. It's just that this part is 0 now. Okay, so here's for a random person enrolled in Stat 200, what's the probability that the person is either in Stat 200 or online? So that's the probability of either in person or online. So that's the probability of online or in person. So the or means we add, and that's the probability of online plus the probability of in person. You could add plus both, but that's the null set. There's nobody in both. So these are mutually exclusive, okay? But how about an example that's not mutually exclusive would be the probability of being online or female. So you could say the probability of online plus the probability of female, and then you'd have to subtract off the probability of both to avoid double counting. Because here's the online, let's say, and here's female, and here's this overlap. So you don't want to count, this is both. So you don't want to count someone who's the females who are online, you don't want to count them here as part of the online and as females. So you have to subtract them off. So this is not mutually exclusive. All right, so here's a nice picture of that. We could say here's online and in person. And those two events are mutually exclusive because being in one excludes the possibility of the other. There also, another word for that is disjoint. And here's if there's an overlapping, if they're not mutually exclusive, and you can be both, the picture looks like this, and here's a good, you could illustrate that with online and female, because you could be both. All right, so let's just do some examples down here. What's the probability here of getting a 5 or a 6 on one roll of a die? All right, on one roll of the die, can you get, so it's the probability of a 5 plus the probability of a 6. How about plus both? Can you get both on one roll of a die? No. So you can't get both, so it's just plus the probability of both, but that's 0. So that's just 1/6 plus 1/6, which is equal to 2, because you can't get both on one roll. How about the probability of a heart or a spade? Again, on one card, you can't, you're just going to add the probabilities, the probability of a heart plus the probability of a spade, because on one card you can't get both suits. So that's just 13 out of 52 plus 13 out of 52, which is 1/2, 26 out of 52, or 1/2. So these events are both mutually exclusive. But let's look at an event that's not mutually exclusive. So that would be, here's a good example of an event that's not mutually exclusive, and that's the probability of getting either a heart or a queen. Okay, either a heart or a queen when you draw a card. So the probability of a heart or queen. All right, so the picture would look like what? There's 13 hearts and 4 queens, but there is an overlap for queens because what? The queen of hearts is both. So you'd have to subtract that off. So it would be 13 out of 52 hearts plus 4 out of 52 queens, but then we want to subtract off 1 out of 52, the queen of hearts, otherwise you'd be counting the queen as both a heart and a queen. So answer is 16 out of 52. What about this? The probability of getting either a 5 on the first roll or a 6 on the second roll of fair dice. So that's the probability of a 5 on the first roll, or, these are all or, so we're adding, or a 6 on the second roll. So it's going to be the probability of a 5 plus the probability of 6, and since you can get both, minus the probability of both. Well, there's 1 out of 6 ways to get a 5, plus 1 out of 6 ways to get a 6, minus the probability of both. Well, the probability, that's the multiplication rule, that would be 1/6 times 1/6. So that would be 11/36. And that's, let's look at, let's go back and look at the table here that we looked at before, and you'll be able to see this better. Okay, so we have this table, and the probability of a 5 on the first is 6 ways. That could happen. 5 on the first, and then 6 on the second. So there's 6 out of 36 ways you can get this, 6 out of 36 ways you can get a 6 on this second, and we are double counting the 5, 6, because that's counted first as a 5, and then on the first roll, and then as a 6 on the second. So you can see that's 11 out of 36 possibilities. So let's go back and do the last. All right, let's do these last two examples. This is the probability of getting at least one 5 on 6 rolls of a die. All right, well, it would be hard to figure it out directly because you could get 1 5, you could get 2 5s, 3, etc. It counts all the possibilities except for what? Getting no 5s. So remember, the probability of at least 1 5 is equal to 1 minus the probability of no 5s. So that's equal to 1 minus, now, not getting a 5, how many ways are there not to get a 5? Well, there's 6 possibilities. There's 5 out of the 6 of them are not 5s, and so it's 5 out of 6, and on 6 rolls raised to the 6th power. So now, here's another one that's difficult to figure out directly, the probability of not all 2s. So instead of doing that, because there's many ways you could get not all 2s, you could get 0 2s, 1 2, 2 2s, just not all 3 2s 3 times. So we're going to say 1 minus the probability of all 3 of them being 2s, which is 1 minus, here's the probability of all, 1/6 times 1/6 times 1/6. So that ends it for chapter 7. Bye.